Exercise 17.7 is asking us to draw a mechanism and predict the products for the electrophilic addition of a hydrohalogen to a conjugated diene. Now, that is going to build on some things from Organic Chemistry 1. So before we start on that, let's go back and make sure we're on the same page about a few really key things from Organic Chemistry 1. First, in order to draw a mechanism, you have to be able to identify nucleophiles and electrophiles. Nucleophiles are things that have a lot of negative charge. So they could either have a full negative charge, a partial negative charge. This is easy to see because it'll be drawn in. This is harder to see. You have to look for differences in electronegativity. Or you could have a place where you have a lot of electrons, like a pi bond or a lone pair. So those are your places where you'll have nucleophiles. And those nucleophiles will attack electrophiles. You'll recognize electrophiles because they'll either have a full positive charge, which is easy to see because it would be drawn in, or a partial positive charge, which is harder to see because that comes from differences in electronegativity. So that's the first thing, identifying nucleophiles and electrophiles. The second thing is classifying carbocations. If carbon only has 3 bonds, then it doesn't have a complete octet. And if you try to find the formal charge for it, it's the column that the group A number that carbon is in, which is 4, minus the number of dots and lines around the carbon. So 0 dots and 3 lines, so positive 1. If carbon only has 3 bonds, then it has a positive 1 formal charge. Now, if an atom ever has a charge, it's called an ion. An ion is an atom that has a charge, and it could either have a positive or a negative charge. If it has a positive charge, it's called a cation, and you can remember that because the T in cation looks like a plus sign. If the cation is on a carbon, then it's called a carbocation. So here we're going to draw a few different carbocations. The first type of carbocation you can draw is a carbocation that has just one carbon next to it. That's described as being primary. And that primary is just referring to the one carbon that's next to the carbon with the positive charge. You could have 2 carbons next to it, in which case it's secondary. It's a secondary carbocation. Or you could have a carbocation bonded to 3 carbons, in which case it's tertiary. So there are 3 carbons bonded to the carbon with the positive charge. In other words, bonded to the carbocation. Now, knowing the difference between being able to recognize a primary, secondary, and tertiary carbocation is important because the more carbons there are around the carbocation, the more stable the carbocation is going to be. So a tertiary carbocation would be the most stable of these 3, and a primary carbocation would be the least stable of these 3. And the reason for that is that hydrogen only has 1 electron. It's not going to be able to donate a lot of electron density to that positive charge to help stabilize it. But carbon has 6 electrons, so it's able to donate much more electron density to help stabilize that positive charge. The more carbons you have, the more electron density can be donated, and the more stable the positive charge is. So that's why a tertiary carbocation is more stable than a secondary, which is more stable than a primary. Knowing those 2 pieces of information, being able to recognize nucleophiles and electrophiles, and knowing the stability of carbocations allows us to review one reaction from Organic Chemistry 1, which was hydrohalogenation. Now the names for those, you'll remember, the names for the reactions are oftentimes very long, and long names in science seem like they're confusing, but actually they're so long because they're not names so much as descriptions. So they seem like confusing names, but actually they're just straightforward descriptions of what you're doing. In hydrohalogenation, you were adding a hydrogen and a halogen to a double bond. So for example, if you had propene, and you add some sort of a hydrogen bonded to a halogen, that's anything in group 7A, so fluorine, chlorine, bromine, or iodine, but usually you would have used chlorine, bromine, sometimes iodine, never fluorine. So here that would be, let's just use bromine. So if you mix those 2 reactions together, you're going to end up adding a hydrogen and a halogen to your molecule, so this was hydrohalogenation. Now, how does the reaction happen? Look for the nucleophiles and electrophiles. In the alkene, we have a nucleophile in the pi bond. In the hydrogen bromide, the bromine is more electronegative, so it steals electron density for itself and has a slight negative charge, and the hydrogen is slightly positive because it's losing that electron density. So that's our electrophile. When you wanted to predict how this reaction was going to happen, you would take that pi bond, the only nucleophile, the only thing that's reactive in that alkene, and it attacks the slightly positive thing, the electrophile, in the other molecule. Now that hydrogen can only form one bond, so if it's going to form a new bond, the bond that it has to bromine is going to break, so those electrons go onto the most electronegative place nearby, which is the bromine. So the first step is that alkene attacking the hydrogen and the electrons in that bond going onto the bromine. So we'll have a bromine floating in space with a negative charge. That negative charge makes it nucleophilic. And then we have that what was propene. And there are two possibilities here. The hydrogen could have added to the carbon on the end, in which case the carbon in the middle lost electrons and has a positive charge. Or the hydrogen could have added in the middle, in which case the carbon on the end lost the electrons, and that has the positive charge. So which of those two possibilities is the one that you get? Well, what we have are carbocations. This one on the top is only bonded to one other carbon, so that is a primary carbocation. This one in the bottom is bonded to two other carbons, so it is a secondary carbocation. And secondary carbocations are more stable than primary carbocations. Those are the least stable, as we talked about. And so the product we got here was the bottom one. We got the more stable carbocation. So how do those two molecules interact? Well, the nucleophile always attacks the electrophile, and so you get your product. You added the hydrogen to one of the carbons in the double bond, and you added the bromine to the second carbon in the double bond. So you added hydrogen and a halogen, in this case bromine, so you did hydrohalogenation. And this was the mechanism for hydrohalogenation that you learned in Organic Chemistry 1. Okay, so we're going to use that piece of information in this problem. The other thing that you want to be able to remember from Organic Chemistry 1 in order to do this next problem, exercise 17.7, is the resonance pattern for an allylic positive charge. You get resonance whenever electrons spread out over more than two atoms. So here, you have a pi bond here between two parallel p orbitals, and next door to it, this positive charge is actually in an empty p orbital. So you have three pi bonds that are parallel on adjacent atoms. So the electrons in this pi bond are actually able to fly over all three of these, which means that the electrons aren't always in the double bond, so it's something less than a double bond, and the electrons sometimes are floating over what we drew as a single bond, so it's something more than a single bond. In other words, you have intermediate bonds here. This bond is in between a single and a double bond, and this bond is also in between a single and a double bond. And in Chapter 2 of Organic Chemistry 1, you learned how to draw those intermediate bonds. You draw them by using resonance structures. Resonance structures draw molecules that have intermediate bonds by drawing false molecules and telling a person to take the average. You warn people that the molecules you're drawing are technically false by including these brackets. Those brackets are big warning flashlights telling the person the true molecule doesn't look like anything inside of here. It only looks like the average of the molecules inside of here. And to just emphasize the point, you drew a special resonance arrow that had one line and two heads. And that arrow means take the average. That arrow is not to be confused with an equilibrium arrow, which has two lines, each with one head. This means that reactants are turning into products, products are turning into reactants, at the same time. Resonance arrow means this structure never exists, the other structure never exists, the only structure that ever exists is the average of those two. In Organic Chemistry 1, you learned a pattern. You learned 5 patterns for when you have resonance and how electrons move when you have those resonance patterns, and those patterns allowed you to predict other resonance structures. One of those patterns was having an allylic positive charge. Allylic means you're one atom away from an atom in a double bond. So here we have a positive charge, and if you go one atom over, you're at an atom in a double bond. So that is an allylic positive charge. And the way electrons move when you have an allylic positive charge is that the pi electrons go toward the positive charge to form a bond there. So to draw the other resonance structure, you would now have a pi bond on the other side, and the positive charge would be on the other carbon. So, one more time, what this means, what all of these symbols here are telling you, is that the true molecule never looks like either of these. It always only looks like the average of the two. So those bonds are all between a single and a double bond, and they all have something in between, so in between a double and a single bond. That's why we have this dotted line there. And then all of the carbons on the ends have something in between a full positive charge and a zero charge. So we have the delta plus there. And so this would be the true structure that these resonance structures are trying to communicate. Okay, so we're going to use all of these concepts to solve this problem next time. This is all stuff from Organic Chemistry 1 that you'll want to remember, and that you'll need to remember in order to solve this next problem. You'll need to remember how to identify nucleophiles and electrophiles, how to recognize the stability of carbocations, the mechanism for hydrohalogenation, and the resonance pattern for an allylic positive.